I'm Elia. Today I want to talk to you about robots. But before I start, of course, science is a team sport. So you see me talking to you now, but without the people you see on this line, nothing would have happened, especially Simone and Ollie, my first co-authors, which are engineers and they work on engineering like me. Um, so we've heard about a self-driving lab in a talk before, in talks before, but so we're all working on the same, let's say, working definitions. To me, a self-driving lab is an integrated system of artificial intelligence, robotics, and analytics that explores a chemical space, in our case, with minimal human intervention. And that means that you have a brain, a machine learning brain, in our case, active learning, that decides what to do, a robot that performs the task, and a set of analytics that analyzes the data that comes out of your process and gives it back to your machine learning brain to figure out what to do next. And as you can expect, even with this little cartoon, a robot can be very, very expensive and very, very complex. Analytics also can be very, very expensive and very, very complex. And machine learning, you can make it as easy or as complex as you want. But in all cases, it can be say, a daunting task to build one of these robots. And I mean, at this moment, I'm speaking as an academic, and I know that there's a lot of industrial partners in the audience, but for an academic that is publicly funded, there should be some public benefit to what we do. And the tools that we build should be really for every lab that wants to partake and wants to try to do what we're doing. And there's an example of this, which is in 2016, a study has been done on North American funding, where 30% of the researchers in the US and Canada get 80% of the fund that's available, which means that if you have a lab that has money, you can throw some money at a robot and do some cool science. But if you don't have that kind of money, you are limited in the cool robotics and cool machine learning you can do. And I also have a very, let's say, close to home example of this, which is our Robochem, the first Robochem paper, where we built a robot that cost us 50K to make plus 180K of NMR analytics. And we can only ever build one of this. We are a decently funded lab. My boss, Tim Noel, relatively famous. But we can't really afford to put one of these on every bench in our lab. So the idea is, okay, I like cars, so I'm going to make a little car metaphor. We want the performance of a Porsche, but we regrettably only have money for a Fiat Panda. So we want to, let's say, empower and close the democratization gap with high performance and low cost robotics, Porsche performance at Panda prices. So how do you do that? Well, I showed you Simone. He's our incredibly, incredibly talented lab technician before. So we take him, we give him a 3D printer, a few months of full creative freedom, and he comes up with these two pieces of hardware. The first one is a 3D printed syringe pump. It's competitive on pressures that it can reach and precisions to what we find on the shops online. And we can make one for $600, which most of it comes from the valves and the motor that we can't really make ourselves. And then we have a 3D printed liquid handler, which is competitive again with microliter precision to what you can find on available commercially, but you can make it with only $450. Everything you see in here that is made with plastic is 3D printed and custom designed by us. And of course, this is kind of the hands and the engine of your self-driving car or self-driving lab in this case. You do need something to react and to do chemistry with. And in our case, we have two examples of this. We have photochemical reactors, which our lab is kind of known for. One of them is this U-flow reactor that was designed a few years ago by some colleagues. And the plastic here is essentially free. It's 3D printed. You can customize angles and everything. And the only thing you have to buy here is a high power lamp, which you can get from Castle for about $300. And of course, a hot plate if you want to do thermal chemistry. And the reason why we did buy a commercial grade one was that when we went to our safety officer in the university and we pitched the idea of building a, let's say, 3D printed, homemade piece of metal that should heat up to 300 degrees, they were not very keen of letting us do that. So we were like, okay, safely, we buy the one that doesn't catch on fire. So you put everything together and you get Robochem-Flex. Robochem-Flex is exactly a liquid handler for making reaction slugs, driving pumps to move liquid through your system, a reactor, a collection for collecting your slugs out, and the possibility of this hub to push your slug to either analytics or directly to your collection slug. And all of it costs you 5,000 euros, which is quite a price drop from the 50K of hardware they needed before, excluding analytics. And of course, because it's a form also matters, we made the RGB compliant, so it has nice little lights that tell you when something's going wrong or something's going well. If you want to see how this works, well, we also have to talk about analytics. And we did have a 180K NMR, and we would have been stupid if we didn't also use that. But the system is made to plug and play with all the analytics we have, given the UHPLC for 80K with MS, or HPLC if you don't have MS, or Araman that we built for 7K, or even, as I mentioned before, human in the loop. It's often that labs have access to shared analytics for the department, or like a GC that they use for multiple things they can't really give to a robot to use whenever it wants, but you can always put samples on it and return your data to your robot. So how does it work? Well, again, you have a planning module. The planning module decides what to do. You get run condition commands. Those get sent to your operation module, which you should have pre-filled with stock solutions. This mixes up a reaction slug, pushes it to your reaction model, which is either thermal or photochemical in this case, and then this gets sent over to your analysis after the reaction has happened, and the analysis analyzes, figures out your key metric of interest, puts it back to your planning module, and given your BO that you're using in this moment or whatever other machine learning methodology you have there, it decides what the next run command should be, and this cycle is repeated until you're happy with your outcome. And usually after this, I go through 4 or 5 different case studies in a very general way to show. Usually my audience is lab chemists, to show what you can do with it. But today, we're an active learning symposium, so I chose 2 case studies of a bit more of a machine learning flavor to showcase the cool thing that BO can do, which is actually solve real chemistry problems for chemists. And the first case is this one. This one is, let's say, the art of data frugality, the art of never wasting a bit of data, because a reaction is expensive for us. It can take up to 90 minutes, plus like 20 minutes of cleaning and making a slug. So it is kind of annoying if you can't really rerun, or like if you need a lot of data to optimize. So we take this reaction where we're trying to reduce this diketone, specifically in this position, and we put it on the robot, human in the loop. So we use HPLC offline, because enzymes that tend to clog inline. So we let this run, and we get in optimized condition where we want a lot of A, we get a 70% yield. We're pretty happy. But as we experiment, we figure out that, as you may have guessed, there's a second ketone there. So our ADH, our enzyme, can attack the other ketone, and we don't want this. And the idea, the way you should see this is, imagine doing pharma, and this is your active compound that you want to sell for millions and millions of euros. But as you react, you see that you have a second compound, and before you can sell it, you have to prove to the legislator that this second compound is not toxic. So what we did is we took all the data we had, we just analyzed it for, let's say, quantifying this second compound as well, which already showed up on our HPLC. And we said to our optimizer, okay, with all the data, before we wanted you to get a lot of A, now we want you to get a lot of B without as much A, so it's easier to purify. And yes, the yields are way lower. We go from 70 to 16%, but it is decently pure, and it actually allows us to purify this, isolate it, and then do characterization. And more importantly, we do see that we have a relatively different position in space, in our chemical space of optimization. For example, we have 2 completely different enzymes. Now, the biochemists suggested this because this enzyme has a slightly, let's say, larger active site, so the more sterically hindered ketone can fit better in there. I don't know. I'm an engineer, so I trust their word. But okay, the first set was this, and we found it very interesting. And then we thought, okay, we're still on this super data frugality. How about we do something different? We do transfer learning. And here we pick a kind of a very, very famous reaction, which is a Buchwald examination, where we make these two molecules. These two molecules are precursor to our antifungal medication. And to do so, we want these two optimizations to live in the same chemical space. So we want the place where our BO can search to be equal and identical between the two. So what we do to ensure this is we take these palladium catalysts that we buy and we featureize them into a two-dimensional UMAP space, taking the let's say features, the DFT features from the Kraken database developed by Aspuro Guzik and colleagues. So we put this catalyst on a space, and now their relation to each other actually means something physically. And then we start doing our optimization. We optimize, we run the first campaign, we do about 20 experiments or 30 experiments, sorry. So we really cover the whole space in initialization. Then we managed to go to a decent 84% in scale up. We're happy with this. And then we're like, okay, now we have the first Gaussian process, the first model. Can we share information within the second model? So we do a little bit more, 4 more initializations, and immediately we see that our optimizers realize that there's correlation between the two models, since effectively it is similar chemistries, and we push to like 90%, 95% yield in small scale and 90% yield at scale up. And the interesting thing is that the robot actually did figure out that for a tertiary amine, you need something like XFOS, and for a secondary amine, you need something like BREDFOS, which is what we already knew from literature, but it's nice to confirm what the chemist already knew from machine learning point of view. Okay, I'm going to leave you with this. The idea was to get Porsche performance upon the prices, and I kind of show you that you can with a bit of inventiveness. And we can't really sell this to you at the moment because we're not a company, but everything is open source. So if you want to build it, you just download the paper, download the files, and get everything in your lab in not too long. And I do need to thank some people that, of course, the organizers for inviting me, you for your kind attention, and the people that were involved in the project. And I don't know if we're doing questions, but if there are, I'm happy to answer any of them.